Okay, so what we said is that we induce current by changing not just the magnetic field, but by changing what we call magnetic flux. So let me write the equation of the magnetic flux here for us to remember. We saw in the previous lecture. The magnetic flux depends on the magnetic field, but also depends on the area of the loop and depends on the cosine of theta, where theta is the angle between the direction of the magnetic field and the direction that is perpendicular to the area of the loop. Okay, so we induce current by making a change in this magnetic flux. In other words, we create a potential difference, we create an EMF by making a change in this magnetic flux. Okay, creating an EMF, creating a potential difference means creating a current. Okay, and what is the equation? The equation for this induced EMF is equal to the change in this magnetic flux, no, the rate of this change in the magnetic flux in time with a minus sign. And why this minus sign? Because we are always opposing. Now the EMF, the current that we induce, they are induced as to oppose the change in the magnetic flux. Well, this equation here we are going to use if our loop is if we have a single loop. Okay, so like this single loop, or it could be a circle. But we are going to use another equation, the same equation, but now multiply by n if we have many loops. Why multiply by n? Well, imagine if instead of just one loop, we have 2, 3, 4. That means we'll have current going through each one of these wires. Okay, so this induced EMF or this induced current will be proportional also to the number of loops that we have, to the number of turns that this wire will be making. Okay, so this receives a name. Okay, it's Lenz's law, which says a current produced by an induced EMF moves in a direction so that the magnetic field it produces opposes the original change in flux. Before we'll talk about change in magnetic field, but it's more than that. It's actually change in flux. How do we change the flux? Well, one way to change the flux is indeed, let me erase this. So one way to change the flux is indeed, as we saw before, by changing the magnetic field. Okay? So in this example that we talked before, what were we changing? The magnetic field, which means changing the flux. Now, so in this case here, where the magnet was very far away means very weak magnetic field. So in this case here, okay, so let me put here case A. In this case A, let me open more space here. Now, so in this case A, when initially the magnet was very far away, our magnetic flux was very, very small. Okay, so our initial magnetic flux was very, very small. As we brought the magnet very close, and now the magnetic field here became much stronger, then our new magnetic flux became much larger. Okay, so this change in magnetic flux causes the EMF, causes the current. Okay, so this change in magnetic flux in this particular case of this example was caused by a change in magnetic field. But let's see some other examples. And this is what we see in this next slide. Other ways to change this flux, okay, the magnetic flux. Well, instead of touching the magnetic field, what I'm going to do now is I have constant magnetic field, okay, homogeneous magnetic field all around. Okay, as you see here in this drawing, okay, so everywhere the same magnetic field, so I'm not touching the magnetic field. What I'm going to touch now is the area. How? Well, suppose I initially have this big loop. I'm going to shrink this loop. Okay, so if I shrink now this loop, let me draw again our magnetic fields, no? The lines of the magnetic field. I'm going to shrink the loop to have something like this. Okay, so initially it was this big loop here, and now I shrunk. So you see that now in this new area here, there are the lines that are crossing this area, fewer lines, no? So the my magnetic flux became smaller. Okay, so initially my magnetic flux was large because we had big area. Now, so this is the initial. Now the final magnetic flux became much smaller because the area is small. No? So I shrunk that loop. What is that going to cause? Well, we will induce a current. We are going to induce an EMF. What is going to be the direction of the current that we are going to induce? Like this. Now it's going to be clockwise. Why clockwise? Because we are going to try to compensate for that change, no? By induce a current that can bring back those magnetic lines, no? Those lines for the magnetic field. Okay, so this is another way to change flux, magnetic flux, and induce a current. I didn't touch the magnetic field in this case. We changed the size of the area of the loop. Okay, so I repeat, we went from this a big area to this smaller loop here. Smaller loop means the lines of magnetic field that were going through this area became now smaller. So we are going to induce a current to bring those lines back. And that means the current will have to be in this direction. So how do you understand that? You have to understand how the magnetic field is created with respect to the area of this loop. Another way to induce current and induce EMF is by changing the angle. Remember, let me repeat here, the magnetic flux depends on the magnetic field. I'm not going to touch it. Depends on the area. I'm not going to touch it. It depends on the angle. This angle theta between the magnetic field, the direction of the magnetic field, and the direction that is perpendicular to the loop. So I'm going to change now. That's another possibility. I'm going to change now this angle. That's what you're seeing on this bottom line here. This is the loop, okay? And we have the magnetic field going through this loop, going into the page. What we are going to do is you're going to rotate this loop, okay? So you're rotating this loop so that we are in this scenario where the direction between the magnetic field and the line that is perpendicular to the area is the same. We are going now to this case where the magnetic field becomes parallel to the area. Okay, so here the magnetic field is perpendicular to the area. Here the magnetic field became parallel. So I go from this initial scenario where the magnetic flux is large to this scenario the magnetic flux becomes zero. That again is going to induce a current. So in the next slide I'm going to illustrate this case so we can discuss what is the direction of the induced current for this case. Okay?